Hello and welcome. This is Dr. Jeremy Mandelkern of drmtutoring.com, and today we're going to be looking at the derivatives of trigonometric functions. If you like this video, feel free to click the like button. You can comment in the comment section. You can also share this video with your friends and classmates if you find it would be helpful to them. There are worksheets available in the comment section of the intro video, including this one. Let's take a look at the key ideas for this worksheet. First, we want to work neatly, especially for longer calculations. And secondly, we can use the implication symbol to organize our work where needed. The use of this symbol will allow us to separate statements where one implies another. This symbol should not be misconstrued as an equal symbol, which is only put in between two expressions that have the same value. We can also take a look at the provided formulas. We have two limit relations involving sine and cosine functions. These are typically proven in slightly higher level methods like using Maclaurin series, or justified using numerical analysis. For instance, plugging in successively smaller values for theta and simply computing these quotients, showing that the quotients approach either 1 or 0, respectively. Of course, that doesn't constitute a proof of these limit relations. If you want a proof, you may need to rely on slightly higher level math, like writing Maclaurin series expansions for sine theta and cosine theta, and performing algebra with the series expansions. We're also provided 6 derivative formulas for 6 trigonometric functions. If we make use of the limit definitions above, then we can simply derive any and all of these 6 differentiation formulas by use of the limit definition of the derivative. We will go ahead and take these to be given and use them in our work today. Let's try this first problem. It reads, if f of x is the quotient sine 2x over x, use a graphing calculator to evaluate the following to 7 decimal places. Remember, the values of the x coordinates are in radians. So the first thing I'll do is make sure we're in radians. We can see that we are in radians, so good deal. And next, we're going to go ahead and start evaluating. So we could do sine of quantity 2 times x, which is going to be 0.2, divided by what was x, which is 0.1. And with that, we'll go ahead and get our value. So then it's going to be 3. And there we go. Okay, that was fun. Let's go ahead and try now f of 0.01. So bringing up the calculator once more, maybe putting it in the corner for this calculation. We have sine of quantity. It's 2 times that x value, so 0.02. And then we're going to divide by the x value, which is 0.01. And we press enter. Okay, so that's equal to, let's do f of 0.001. It looks like maybe this expression is tending to 2, I would guess. So we're not proving that with these numerical calculations, but we're kind of suggesting it strongly. So here we go. We got sine of 2 times 0.001, so it's 0.002. Quantity divided by 0.001. And well, that's really not much different from the last calculation. So it's 5 9s, an 8, and a 7. And just like that, we have done the numerical aspect of this first question. Okay, because we're rounding, we may want to use like an approximation symbol, is approximately equal to, because those are not exact values. And we're going to use the above answers to make a conjecture about what is this limit as x goes to 0 from the positive side. Well, based on this evidence above, I think 2 is a reasonable assertion. So the limit is 2. Actually, we can do this algebraically. So we'll also justify it graphically. Right now, we're going to use a graphing calculator to graph the function. That won't really confirm your answer, but it will give just some more backing for the claim that the limit is 2. So I go to y equal to, and I type in sine 2x quantity divided by x. And we go ahead and produce the graph. We're not going to play with the window here. We'll just see what this looks like. You can see that really not much detail. Maybe we can zoom in on this little pimple in the middle here. So we'll go to window and we'll make this maybe from like -4 to 4. And we'll graph in a square box. So that way we don't get any distortion of the graph. So this is from -4. It's kind of arbitrary to pick 4, but we'll see if this produces more clarity. And there you go. Okay. Well, it looks like from this picture, as x goes to 0 from the left and from the right, so as we approach 0 from the left and from the right, yeah, it looks like those y values are tracking up towards 2. So I think our assertion that the limit is 2 is supported from this graph. So it looks like the limit from both the left and from the right is the same. So we can say that, yeah, this is kind of like justified from the graph. And we'll just go ahead and say, see our wonderful, beautiful graph that we had produced. So see the graph here from the TI. I'm not going to go ahead and reproduce it right here. Real rebel, breaking their rules. So we'll just go ahead and refer to the TI. Now, as far as how you would prove this, well, I think we can prove this using simple algebra and using one of the limit relations above. We actually know that, okay, we were kind of told that the limit as x goes to 0 of sine x over x is equal to 1. Okay, that was provided to us at the beginning of this worksheet. So can't we just go ahead and do simple algebraic manipulations? So f of x is sine of 2x over x. I'm thinking of making a funny change of variables and also introducing, okay, that is not right. That's a typo. So let's go ahead and fix that. So just whoopsie daisy. So I'm thinking of going ahead and just adding in like a factor of 2 right there. That's highly illegal, obviously. I would need to also multiply by 2. And then I'm going to do some funny business. I will write this function a little more suggestively. So it's 2 times the quantity sine of 2x over 2x. And we know that the limit as x goes to 0 of f of x is therefore equal to the limit as x goes to 0 of this expression. I want to use the property of limits that permits us to grab multipliers, constant factors, and pull them out in front. Okay, so this gives us the following. We have this is equal to 2 times the limit as x goes to 0 of sine 2x over 2x. Now, I really want to use the formula that is appearing right here, this boxed formula. So I want to use that. How can we use that? So I think we're going to change variables here. So we'll go ahead and let 2x be a new variable. So my suggestion is call this maybe like w. So that's a W as well. And I think it's pretty easy to justify that as x goes to 0, so does W. So the limit that we want to find, therefore, it's going to be equal to, right? And it's not too hard to motivate that in terms of W, as x goes to 0, so does W. So we can see the use of the boxed rule above, but with x replaced by W. And for this reason, we get 2 times 1. So this is in agreement with what was justified numerically, yet this work right here is a little more rigorous, and it doesn't require us to make a jump from the values seem to be approaching to the claim that the value of the limit is 2. So there we have it. We have now solved yet another calculus problem. Let's try this second problem. It reads, find dy dx for the following functions. First, in part A, we have secant x times tangent x function. In part B, 4 cosecant x times cotangent x function. Well, I think we should be using the product rule to differentiate. Here we have dy dx. It is the derivative of the secant function times the tangent function. So you can see here on the right, I've already written the derivative of the secant function. So let's put that in quotations. This is secant of x times a tangent of x. That's going to be multiplied by just the second function in the product there, so tan x. And according to the product rule, we should add the derivative of the latter function. So the derivative of tangent is secant squared of x, that's secant x function squared, times what is the first function, which is another secant of x. When we go ahead and simplify this, we wind up with what is secant x times tan squared x plus secant cubed of x. We could probably leave our answer in this form. There is a way, though, that we could write our answer solely in terms of secant functions. So the way to do that is to drum up the Pythagorean identity involving secants and tangents. So from the identity that sine squared of x plus cosine squared of x is equal to 1, we can go ahead and divide both sides of this equation by what is cosine squared of x. And we wind up with the identity, which is tan squared of x plus 1 is equal to secant squared of x. So my recommendation is to eliminate this factor of tan squared. We can replace it by secant squared of x minus 1. And we get then the final result. It is secant x times secant squared x minus 1 plus secant cubed of x. And you can see that there's actually 2 secant cubed x terms. So I'll write a final version and then leave it alone. So it is 2 secant cubed of x. And there's also a minus secant x as well. And with that, we have solved part A. Let's try part B. We'll put a little bit of a partition right there. And writing in, say, the color green, we have dy dx is equal to. I think here we can tag this 4 onto the cosecant x, like pin it to the cosecant x in the front, and we'll treat that like a front function times a back function. So it's going to be another product rule. We have the derivative of 4 cosecant x. So fortunately, on the right, we have these useful rules. The derivative of cosecant x is minus cosecant x cotangent x. So this is going to be what is 4 times a minus cosecant x times cotangent x. And that would be times the latter function, which is cotangent x. And then this is the product rule, so we're going to add the derivative of the latter function, which is a minus cosecant squared x, times the former function, which is 4 cosecant of x. We want to simplify this if possible. So our first version involves just kind of cleaning up these terms a bit. It's minus 4 cosecant x times what is a cotangent squared x. And then there's another term which is minus 4 cosecant cubed x. I have a feeling we can do a similar simplification as we did before using a Pythagorean identity. I believe there is an identity relating cotangent squared of x to a cosecant squared of x. We want to get that identity written correctly. So to the right, we'll go ahead and from the sine squared x plus cosine squared x is equal to 1. This time, let's divide both sides by sine squared x and just see where it takes us. I believe this should generate the Pythagorean identity that we need right now. This gives us 1 plus cotangent squared x is equal to cosecant squared of x. So it follows that cotangent squared of x, this factor right there, can be replaced by cosecant squared of x minus 1. So writing our result, we have what is minus 4 cosecant of x times what is a cosecant squared of x minus 1. And this is then take away 4 cosecant cubed of x, our final result for that one. Then when the dust settles and the smoke clears, take a look. We got minus 4 cosecant cubed of x. And then there's another minus 4 cosecant cubed of x. So a total of minus 8 of these cosecant cubed x. And we finally have a plus 4 cosecant x. So that's quite nice, writing our answer in terms of a single trigonometric function. And with that, we've solved problem number 2. Let's try problem number 3 next. So here, for problem number 3, we're tasked with finding some first and second derivatives of the given trigonometric functions. I suppose we could use the color black for this calculation. So here, with y equal to secant x, so d dx of secant x is something we've already used. That is secant x times tangent x. This means that d squared dx squared of y, the second derivative of y with respect to x, is going to be the derivative with respect to x of the first derivative above. So we'll differentiate using the product rule. The derivative of the secant function in the front, the derivative of the secant function in the front, that is secant x tan x times a tan x. And we're back. We were just about to compute the second derivative of y with respect to x. So we're using the above first derivative calculation and applying the product rule once more. So differentiating the secant x gave us the secant x tan x times just the second function, which is tan x. And then we're going to add the derivative of the second function, which is a secant squared of x. And that will be multiplied by just the first function, which is secant of x. We can clean this up a little bit. Here we see that there's a little bit of simplification. This is secant x times what is tan squared of x plus secant cubed x. If we really want to, we could also write our answer solely in terms of secant functions. And that is because we know that tangent squared of x is equal to secant squared of x minus 1. So as an option, we could potentially replace this tan squared of x by secant squared of x minus 1. And we could then distribute the secant in. We're going to then get a final answer, which arguably is more simplified. I don't know. It's going to be what is a secant cubed of x plus another secant cubed of x. So it's 2 secant cubed of x. And there's also going to be this minus secant x expression as well. Okay. Here we've gone ahead and successfully differentiated twice the secant x function. Let's try now here differentiating twice the tangent function. So for both a and b, we are to find y prime and y double prime. So we can make a little divider here. And we'll try here d dx of what is tan x. So we know that this is a secant squared of x. This can be derived, if we so choose, by writing tangent x as sine x over cosine x, and then using the quotient rule and just simplifying using quotient identities after using the quotient rule. We'll take it as sacrosanct that this derivative formula holds. It's going to be valid wherever here the tan x function does not have a vertical asymptote. So there are certain x values like plus or minus pi over 2, plus or minus 3 pi over 2, and so on, where this relation is not valid. So we can just clarify here that a statement like this, it's valid where the left and right-hand side are defined and real numbers. So this is valid for x not equal to the troublesome values of plus or minus pi over 2, plus or minus 3 pi over 2, and the list goes on. So we're going to now wrap up with doing our second derivative. So d dx of what is a secant squared of x would be the derivative of the derivative. So this gives us, by inspection, well, what rule to use? How about we use a product rule? So we have secant x times itself. So the derivative of the first is going to be secant x times tan x times the second. And then we're going to add the derivative of the second, which is another secant x times tan x times the first, which is secant x. So we wind up here with what is 2 secant squared of x times tan x. I suppose we could replace the secant squared by tan squared x plus 1. So this is going to give us an answer solely in terms of tangent functions. So this will be replaced by tan squared x plus 1. And we'll just scroll down to have a little more space. So the final result is going to be then looking like what? So it'll look pretty nice, I think. So there is going to be a 2 tan squared x. There is also times a tan x. So when that is all multiplied out, it is 2 tan cubed of x. And finally, we have 2 times a 1 times a tan x. So that is plus what is 2 tan x. I believe that is fully simplified. You may argue that it's even looking nicer with the secant squared x. I think it's a matter of opinion, and we want to present our answers in mathematics to either specifications given, or we use our good judgment when there are no specifications given. We can say that these two answers are both okay, and we should probably label as such which one is y double prime and which one is y prime. So this one right here is going to be the y double prime, whereas y prime is right here. So now it is as clear as day, I believe. All right, let's go ahead and move on to the next problem. So we have a few more to solve today, and you can see there's actually quite a bit on the worksheet. So let's just take it one problem at a time, which is always a good strategy in math and in life. Just focus on the obstacle in front of you and try to overcome it. So this one reads, find f prime of x, and then find f prime of pi over 2. Given that f is this product function, you got a polynomial times a cotangent of x function. So the first thing we'll go ahead and do is compute f prime of x. The rule that we should use is the product rule. So we can't label the two functions in the product as f and g because f is already taken. We could use u and v, I suppose. So that could be the u function, and that could be the v function. And we have then that the derivative of u times v, we know d dx of what is u times v, where u and v are functions of x, is u prime v plus v prime u. So with that in mind, we'll go ahead and write out these terms, starting with the u prime v. So differentiating the polynomial with respect to x, we get what is 8x plus 4 times a cotangent of x. And then we'll write our plus symbol. The derivative of the cotangent function is minus cosecant squared of x, and that will be multiplied by the function u, which is the original polynomial presented in the question. I suppose there is some algebra that could be done here, but I recommend leaving your answer in this form. It is somewhat instructive in that you can kind of see the building blocks from that product rule calculation. As far as f prime of pi over 2 is concerned, we're hoping for simplification in the cotangent function as well as the cosecant function. Aside, we know that cotangent of x, that is going to be equal to what is cosine over sine. So that is cosine of x over sine of x. Whereas the cosecant function, that is the reciprocal of the sine function. So it is quite common to blunder and indicate that the cosecant function is 1 over cosine. You see the C and you think, oh, cosine, but that is not the case. It is a little counterintuitive, the naming of the cosecant function. It is 1 over sine. Now, let us go ahead and evaluate very meticulously. So we're plugging in pi over 2 in for x, wherever we see x. So 8 times pi over 2 gives us what is 4 pi plus 4. When we evaluate the cotangent function, that is, when we evaluate the cotangent function at pi over 2, we have cosine of pi over 2, which is 0, over sine pi over 2, which is 1. So this is a factor of 0. And then we have plus what is minus the square of cosecant of pi over 2. So when we do cosecant of pi over 2, it's 1 over sine pi over 2, which is 1 over 1, so it's 1. Now, important is that we're squaring not the minus symbol, but just the cosecant of pi over 2. So we're going to get that minus 1 times the square of 1. And lastly, we plug in the pi over 2 for x. We get very meticulously done. It's going to be pi squared over 4 times 4. So that's pi squared plus 4 times pi over 2. So that is going to be a 2 pi. And I do think it's worthwhile to write a final version since the whole first term is kind of just canceling out. Now that term goes to 0. And we're just getting what is a number value. It is minus pi squared and also minus 2 pi. And there is our result. I am being human, only subject to hear the errors that all humans will make. So contrary to popular belief, I am not a robot. So if I do make a blunder and I don't catch it, then please do leave a comment in the comment section if you feel that was a typo made, if 1 plus 1 is written to be 3, and so on. So I'll do my best to weed out these blunders, but it is somewhat inevitable that in mathematics, when we're writing solutions, especially when we're working under some conditions like a prolonged period of time and tiredness or fatigue, attrition can set in, and that's where the blunders are going to creep in, especially when we lose our concentration in longer problems. So for problem number 5, it reads, compute the derivative with respect to x of this quotient function. Because f and g are not taken, I think it's a good idea to just call all this stuff f. This is probably going to be a bit of a monstrosity when we're done. And we might not have hopes of simplifying much. So we'll call that one right there function f. And the bottom one, we can call that function g. By doing this, we can see this accents the fact that this is a quotient of two functions, f and g. So we want to apply the quotient rule. And let's dive in. So the derivative of the quotient of f over g, we know d dx of f over g. That is f prime g minus g prime f, all that over g squared. So very meticulously, we start writing out what this is. I'll just go ahead and extend the equal symbol right there. And we have first f prime. So to do f prime, we're going to have a product rule since f in itself is a product. So the derivative of what is the function in the front, the 12x cubed, gives us 36x squared times cosecant x. This is multiplied by the second function. So we've already done the times cosecant x. Then we have what is a plus. I don't think necessarily I need the parentheses to be drawn yet so that we can fix that. So we'll make the entire product rule within parentheses. So here's a plus. And times the derivative of cosecant, which is going to be a minus cosecant of x times cotangent of x. And this is multiplied by a 12x cubed. All that was just the derivative of the top function. Now, this in turn should be multiplied by the bottom function. So we have the f prime g. So we'll put some brackets. And this is 3 sine x plus 3x to the 4th. And this is still the numerator. We'll do minus here. And we need to do the g prime times f. So let's again put parentheses to do g prime. It looks like it's more straightforward. It is 3 cosine of x plus what is 12x cubed. Next, we'll go ahead and multiply by what is function f. So that is 12x cubed times cosecant of x, and we have that cosecant of x. And notation is so-so here. Of course, cosecant of x and cosecant parentheses x are the same. There's no real reason to differentiate between those, but here it's okay to include them both in the expression. Finally, we divide by the square root of g. By the time we write this, we're not going to want to do any algebra to simplify it because it's going to be so messy. So 3 sine of x plus what is 3x to the fourth quantity squared. And I suggest we should just leave this alone. So this is like, okay. The problem was from the get-go destined to have a very messy answer because there was a lot going on in the original function that we set out to differentiate. There may be shortcuts sometimes. Here, I would mention that there is a technique known as logarithmic differentiation, which says before you differentiate, first take the logarithm of the expression you want to differentiate, use properties of logarithms to simplify, and then and only then do you differentiate. And then you must somehow undo the logarithm step in the beginning at the end. But as it is, I don't think that was wholly necessary for this problem. So we just went ahead and used the quotient rule. There was a little bit of a complication where we had to use the product rule in the numerator when we differentiated the f function. Other than that, it was okay. So let's go ahead and move on. So we have the next one. Use the definition of the derivative to calculate the f prime of the cosine x function. And we're giving a trigonometric identity. So it is a sum formula for finding the cosine of a sum of two angles. Let's see how it works out. So we have d dx of cosine of x per the rule above, that is the limit as h goes to 0 of, so for f of x plus h, that's clearly going to be cosine of x plus h. And that should be enough room, I think, for the calculation. So we have cosine of x plus h minus f of x, so cosine of x, and all this over h. I think we can all see here where we could use this sum formula in the hint. So particularly on that term right there, we could take A quantity to be x and B quantity to be h. So assuming that that identity is written correctly, we would have the following. So drawing a big division bar, because this is going to get a little bit longer now. We have the following. So it's going to be cosine of A, so it's cosine of x, times cosine of B, so it's cosine of h, minus, we have sine of A, so that's sine of x, times sine of B, so that's sine of h. We're going to take away from that cosine x and divide by h. I committed a cardinal sin here, which I think you'll spot. So what is the cardinal sin that Dr. M has committed? He has dropped his limit. So we can fix this. So we'll just kind of patch it in right here. So it is limit as h goes to 0. We're back on track. So as far as the simplification of the numerator is concerned, I think we should try to group together maybe terms. I see that there are a couple terms with cosine in it. So I'm not exactly sure the algebra from here. So we're going to wing it. Maybe these two terms can be grouped together. and we can factor out a cosine of x. That's my suggestion. So let's see if that is successful. So we have the limit as h goes to 0 of huge division bar. So there we go. And we have what is cosine of x multiplied by what is cosine of h minus 1. There is also, by inspection, a minus sine of x times sine of h, and this is all divided by h. I guess I did not need such a big division bar. I think the next thing to do is to realize that a limit will distribute across a sum or a difference provided the individual limits exist. We don't know if these individual limits exist, but we can go ahead and check by distributing the limit across the sum or the difference, in this case, the difference. And then after the fact, we'll justify whether that was okay. So I'm going to distribute this limit symbol across the difference to give what is cosine x pulled out in front times a limit as h goes to 0 of cosine h minus 1 over h. And we also have, why don't I write that cosine of h, the h in parentheses. There is a function called the hyperbolic cosine, which might kind of look like COSH, so that looks better. And now we also have a different symbol. Sine x does not have any h's in it, so we can pull that out. So that's sine x times the limit as h goes to 0 of sine h over h. And I do believe that these are stock limits. We can look them up. So this one can be justified numerically to be 1 as h gets closer and closer to 0. Sine h over h approaches 1. You can also validate that one using more advanced math, like a Maclaurin series for sine h about, this h equal to 0 expansion using a power series, and then maybe doing termwise division and applying the limit. That may do the job. You could potentially use other techniques altogether to try to justify this proof that this is 1. We're going to take that to be sacrosanct. And as far as the other one is concerned, I believe that one is 0. So we can also use similar techniques, I suppose, to prove this. You would not be able to use standard algebraic methods to establish this limit. Definitely, though, the so-called L'Hopital's rule, which we have not covered yet, would be a good way to validate these limits. So I'll just make a claim that these assertions of the values for these limits, these assertions, they can be proven using a slightly more advanced method, for instance, like L'Hopital's rule. L'Hopital was one of the originators of calculus around the time of Newton, and reportedly he put out the first calculus textbook, and that is significant. So the originators, Newton and Leibniz, did not necessarily here make calculus available to all. It was probably as much the work of their followers. Those that followed the work broadened it and then made it widely available, like L'Hopital, through the textbook that he produced. So when we simplify, we have here what is minus sine x, and this agrees with the known formula for the derivative of the cosine function. So we can give this kind of like a check, check, check. I hope you found that informative. We have perhaps one more problem to solve in our calculus worksheet on the derivatives of here, the trig functions. And it's been a wild ride so far. We actually just used these limit formulas in our work. Let's take a look at this last problem. It reads, use the known derivatives for the sine x and cosine x functions to derive the formula for the derivative of cosecant x by using the quotient rule and known trig identities. So we know that cosecant x is 1 over sine of x. So I suppose we can call the f function 1 and the g function sine x. So aside, we know d dx of f over g is equal to f prime g minus g prime f, all that over g squared. So it returns then, upon applying this rule to the right, that the derivative of cosecant x is going to be f prime, so that's a 0, times g, so it's times sine x, minus, well, g prime, we can use the known formula. The derivative of sine is cosine function. So this is cosine of x times f function, and all this is divided by what is the square of g. And I think we're about there. So the square of g is sine squared of x. We simplify this to get what is in the numerator minus cosine of x over sine squared of x. And I think we should further clean this up. Well, cosine over sine is cotangent of x. So this is minus what is cotangent of x times 1 over sine x. But 1 over sine x we know to be cosecant x. So we write our final version as maybe minus, I'll permute the factors. It's cosecant of x times cotangent of x. And that agrees with the results given in the formulas of this worksheet. And with that, we have solved yet another calculus worksheet. I hope you enjoyed this video on the derivatives of trigonometric functions. Please stay tuned for more videos. Please stay tuned for more videos on calculus and solving calculus problems through worksheets. Learning calculus through worksheets is a great way to understand what can be otherwise some daunting material, and seeing somebody who's been doing this work for many years, seeing them write their solutions to these very topical problems within calculus should give you the confidence to do it yourself. That's why also I've provided the worksheets for you to try these problems yourself, and you have the videos to see the solutions if you get lost along the way. If you like the video, you can go ahead and subscribe to the channel. You can click the like button, and you can share this video with your friends and classmates if you think it'll be helpful to them. Thanks for joining me, and bye-bye.